So basically, there are four type of number systems in digital, which we are going to discuss. First one is binary number systems, and second is octal, and third is hexadecimal, and fourth is decimal. So I'm planning to discuss this number system topics in a brief manner so that we can complete these number systems as soon as possible, and we can go into combinational circuits and discuss them in detail. So is it okay for everyone? Right, is it okay?
Yeah.
Yeah.
O-
So
Okay.
yeah, so binary number systems is are the number systems with base 2, and octal number systems are of base 8, and hexa are of base 16, and decimal are of base 10. So binary numbers, in case of binary number systems, we have only two digits, that is 0 and 1, whereas in octal we can represent numbers from 0 to 7, and in case of hexa we can represent numbers from 0 to 15, and in case of decimal we can represent decimals from 0 to so on. Like decimal is our regular number system, we can represent from 0 to infinite. So here we can see that in case of binary number systems the base is 2, so we are representing the numbers in 0 and 1. So for base 8 it is 0 to 7, and hexa, that is base 16, we are representing from 0 to 15, and here, yeah, so that's the partition of this number systems: binary, octal, hexa, and decimal. And also we have BCD number systems, that is binary coded decimal number systems. Here we represent the numbers from 0 to 8, sorry, 9. So in BCD we will represent the numbers from 0 to 9. So now let's start with our binary number systems. So in case of binary number systems, the base of the number is 2. So basically, if there is a number, this is a number, and the base is the sub, this one. This is a base. So this is base 2, which means a binary number. So if, we will directly start with the conversions of binary number system to decimal, binary to octal, and binary to hexadecimal, and binary to decimal. So before going to talk about the conversions, so we all know that binary number systems are basically used in computer language. So basically machine will understand only binary number systems, that is zeros and ones, and these binary number systems are so we use decimal number systems. So we will convert this decimal number systems. The simulator will convert our decimals to binary, or our simulator will convert our hexa to. Finally, the last will be our binary. The simulator can understand, or the compiler can understand only binary language. So this is what I want to discuss, and we will start directly with the conversion of binary to decimal number system. So if we have a binary number, say 0 0 1 1 0 1 to the base 2. So binary, in binary number systems we will have only zeros and ones, and if we want to convert it into a decimal number system base 10, then we simply uh, add the weights of individual digits, that is here 1 into 2 power 0, this will be equal to 0 into 2 power 1, and here it will be equal to 1 into 2 power 2, and this will be equal to 0 into 2 power 3, and this will be equal to 0 into 2 power 4. So finally if we add the weights of individual digit, then it will be equal to 1 plus 1 into, sorry, 0 into 2 power 1 is 0, plus 1 into 2 square is 4, and all rest all are 0. So it will be equal to 5. So the equivalent of double zero, wait a minute, here I have missed it, 0, 1, 2, 3. So it will be equal to 1 into 2 power 3, sorry, plus 8. So 8 plus 4, 12, plus 1, 13. So it will be equal to 13 to the base 10. So the equivalent of double zero double one zero one to the base 2 will be equal to 13 to the base 10. So this is how we convert any binary number to an decimal number. Or else we have another method which is called 8421 code. So this is an method to convert binary number system to decimal number system. So if we have a 4-digit binary, say suppose 0110, and if we want to convert it into decimal number, then we will apply this 8421. So we will add the corresponding weights, that is, this is equal to 4 and this is equal to 2, so it will be equal to 6. So 0110 is nothing but 6 in decimal. And if we have any fraction, say suppose 1011.010, and if we want to convert it into a decimal, then for the integer part we will follow the same method of adding the weights of particular digit. It is 2 power 0, 2 power 1, 2 power 2, and this is 2 power 3. So 1 into 2 power 0 plus 1 into 2 plus 0 plus 1 into 2 power 3. So we will get 1 plus 2 plus 8. 8 plus 2, 10, plus 1, 11. Or else we can use this method. This will be 8 plus 2, 10, plus 1, 11. So integer we are getting 11. So for fractional part, we will take, this will be equal to 2 power minus 1, this will be equal to 2 power minus 2, and this will be equal to 2 power minus 3. That is 0 into 2 power minus 1 plus 1 into 2 power minus 2 plus 0 multiplied by anything is 0. So we will get 1 by 2 power 2, which is equal to 1 by 4. So 1 by 4 will be equal to 0.25, I think. Yeah, 0.25. We have another bit, then we will take here 16. Then it will be equal to 16 plus 420 plus 2, 22.
Yeah, okay.
So if we have a fractional part, then it is equal to 1 into 2 power minus 2, that is 1 by 4, 0.25. So finally the equivalent of 1011.010 will be equal to 11.025. So this is the equivalent in decimal. So this is the process of converting binary to decimal number systems. So is there any doubt in this? Can we move forward?
No.
Thank you.
Yeah.
So wait a minute, let me add some more slides. Yeah. So coming to vice versa operation, that is decimal to binary number systems. So if we have a decimal, say 100, and if we want to convert it into a decimal number, then we will use repetitive division method. That is, we will take this 100 and divide it by 2. That is, 2 into 5 will be equal to 10, 0, and the remainder is 0, and followed by 2 into 25 is 50, remainder is 0, and 2 times 12 is 24, and the remainder is 1, and 2 times 6 is 12 and the remainder is 0. 2 times 3 6, remainder is 1, sorry, 0, and 2 times 1 is 2 and the remainder is 1. So like this we will follow the repetitive division, and we should take from bottom to top. We will consider the number from bottom to top. So generally we will get confused in this, so we should remember we will take the number from bottom to top. So finally the equivalent of 100 will be equal to 1 1 double 0 1 double 0 to the base 2. We should be careful here, we will generally forget this, that is from top to bottom or bottom to top. So for integers we should consider from bottom to top. So the equivalent for 100 to the base 10 is equal to 100 100, and if we have a decimal associated with it, say 100.5 to the base 2, sorry, base 10, we want to convert it into base 2, then for the integer we will follow this repetitive division, and for decimal we will follow repetitive multiplication, that is zero point 0.5 into 2, which will be equal to 1.0. We will consider the integral part, sorry, we will consider the fractional part, and we will neglect the integral part. So in the next step it will be equal to 0 into 2 will be equal to 0, and again we will take the decimal part only, that is 0 0.0 into 2 equal to 0. So we will do this repetitive multiplication until we get a 0, or we will, if we are not getting 0, so we will stop at some point. So in this we will consider this integral part from top to bottom. So here we will consider from top to bottom. So finally the answer will be equal to 1100 double 100 100 point 100. So this is the equivalent of binary of 100.5 to the base 10. So this is a conversion of decimal to binary number systems. So is this clear for everyone? So is there any doubt? Can we move?
Yeah, clear.
So coming to we have discussed binary to decimal and decimal to binary. Now coming to octal to binary. So now we will discuss octal to binary. So octal numbers are the numbers with base 8, and we have octal numbers from 0, starting from 0 to 7. So if we have an octal number, say 73 to the base 8, and we want to convert it into base 2, then we will first, the first step is we should convert each digit into binary. Say suppose for 3, the equivalent binary we should represent in 3 bits. The equivalent binary should be 3 bits. So for 3, the equivalent binary number is 0 1 1. With the help of 421 code, we will write the equivalent of this digit. So 3 is equal to 2 plus 1. So at 2 and 1 positions we will make 1, and at 4 we will make it 0. So for 3 it is 0 double 1, and for 7 it is equal to 111. So if you don't know how to write the equivalent of 7 in binary, then take the help of this 4 to 1 code. So 4 plus 2 6 plus 1 will be equal to 7. So finally 73 to the base 8 in binary is equal to 111. Wait a minute. 111 followed by 0 double 1 to the base 2. So this is how we convert an octal number into a binary number. And if we have, sorry, added many slides. Wait a minute. So if we have a binary number, say 56.78, sorry, 75 to the base 8, and if we want to convert it into binary, then the same process for integers as well as fractionals also. So here 6, the equivalent of 6 is 0, sorry, double 1 0, and the equivalent of 5 is equal to 101. Take the help of 4 to 1 if you are not comfortable to write directly. And for the fractional part, we have 7, which is equal to 111, and 5, which is equal to 101. So finally we have the equivalent of 56.75 to the base 8 is equal to 101,110.11101 to the base 2. So this is how we convert octal to binary number systems, and vice versa process, that is octal to, sorry, binary to octal conversion. So if we have a binary number, say 1101 uh, 0 1 1, so this is our binary number. I will take another one. And if we want to convert it into an octal number, then we will make a group of 3 in this binary number. So 1 1 1 0 1 0 1 1. So this is a group of 3, and 101 is a group of 3, and we are left with 2 digits, so add a 0, so to make it a group of 3. So the equivalent of 011 is equal to 3. If you are not comfortable with it, to directly write the equivalent, then take the help of this 4 to 1 code. So equivalent of 011 is equal to 3, and equivalent of 101 is equal to 6, and this is equal to 3. So the equivalent of 11101011 to the base 2 is equal to 363 to the base 8. So this is how we convert an binary, we convert a binary number to octal number. Similarly, if we have some decimal, also the same process. So if we have, sorry, binary also, it is the same process of converting it to an octal number. So make a group of 3, this is equal to 6, and here we are left with only 2 digits, so add a 0 after it in the LSB. Whereas in case of MSB, if we are left with we are if we have less than 3, then add a 0 at the MSB, whereas in fractional part add a 0 at the LSB. So here it will be equal to 4 plus 2 6. So it is equal to 66 to the, sorry, 6.6 to the base 8. So this is how we convert a binary number to an octal number. So is this clear for everyone?